Hello. In this video, we're going to be looking at an application of integration. Now, it is a physics application, and it is work. So, in these problems, we're going to take a physical phenomenon, such as a spring or pumping fluid out of a tank, and we're going to see how much work is used to pump the fluid, or how much work the spring does on an object to pull it up or push it down. And what we're going to use is the physics formula, work is equal to force times distance, and work equals Fd, or W equals Fd. Now, we're going to have to make an assumption here. And our assumption is that our field is conservative. Okay, so what does it mean for a field to be conservative? Well, say I have a gravitational field, and I have a box. Now, if I move the box from the ground up to another height, I apply some work on it. So, the work here is equal to force times distance. Now, if I have the box at a certain height, say the same height, and I move it down, the work that is done by gravity is also equal to force times distance. So that's saying that if I move an object from point A to point B, and then I move it from point B to point A, I'm actually doing 0 work total. So work total is equal to 0. Now, this is going to be useful when we do our integration, because if we have, say, an object and we're applying a force to it, and the object starts here and then does some crazy stuff, loops around, and ends here, all we have to do is find the work done from point A to point B, and we don't. Now, the formula W equals Fd assumes that our force is constant over the entire length. But say I'm moving my box, and I start by applying a force of 5 newtons. And then later on, I start to get tired. So I move the box another distance, but I'm only putting 3 newtons on it. And then I finally come to rest. Now my force has changed. So we have a force is actually going to be a function of the distance. And to find the total work, we're actually going to integrate from point A to point B of f of x dx. Now, in our example, when we had this nasty loop, we would actually have to do a path integral to figure out the force on each of these little small intervals. We don't have to worry about that because we're in Calc 2. Once we get to Calc 3, we'll actually have a much more difficult time. So our final assumption is that our force is going to actually be a function, and it might be a straight line, it might go up and down, it might be constant. Then we can just use work is equal to force times distance. But in every case, it's just going to be a function of x. So the example that we're going to look at now gave me a lot of grief when I was taking Calc 2. And it still gives me a little trouble to this day. So we're going to work through it together, and we're going to pump fluid out of a spherical tank that's buried underground, and we're going to see how much work it takes to pump it out. So let's get into the problem. We have a spherical tank with a radius of 4 meters that's half full of oil. And the density of the oil is 800 kilograms per meter cubed. Now, this makes sense because oil is less dense than water. Water has a density of about 1,000 kilograms per meter cubed. And this tank is buried 1 meter underground. And what we want to know is how much work do we need, or how much work is required to pump all of the oil of this half-full tank to the... So let's start by looking at the tank itself. So I've drawn a sphere and I've drawn the pipe. And we know that work is equal to the integral from A to B of some force function times some distance function dx. So what we need is we need our force function, we need our distance function, and we're going to need to figure out what our bounds are. We're going to need those A and B's. So looking at our sphere, we know that it has a radius of 4 meters. Now, we're going to need axes here because we need to get some coordinates to actually integrate with. So let's just make the center of the sphere our x-axis. And we'll make the y-axis going right through that, right through the center. Okay. Next, we need to know how much are we actually pumping out at any given moment. So if we look at a slice of this sphere, so what we're going to do is we're going to take the fluid that's located in the sphere and we're just going to see how much work it takes to pump up each little slice. So if we were to look at a slice of this sphere, say, let's make it just a little thicker, we're looking at this little slice here. And if we look at this, it looks, when we get in really close, if our height is really small, it looks like a disc. So it looks like a disc. And as we know, a disc is just a cylinder. With a really small height. So let's go ahead and get ourselves into writing mode again and take a look at the volume of a disk. Well, it's a circle with a small height, so it's going to be pi r squared h. So our height is just going to be this very small increment dy that we're pumping out. So our h is going to be a dy, pi is still pi, and now we have to figure out what r squared is. So our r has to be some function of y. So we know, so we just need to know the radius at this slice. So what is this radius? And let's just zoom into the sphere. Our radius is what we need to find. Okay. And let's zoom to the appropriate magnification. So we know that this is a circle in total. And as we go up or down, we're going along the slice that we see of the circle. So we know that x squared plus y squared is equal to r squared. And we want to solve for y. Okay. We also know that the radius is 4 meters, so we can replace this r squared with 4 squared. So solving for y, we get y squared is equal to 16 minus x squared, or y is equal to the square root of 16 minus x squared. And that's our radius of our disk at any height y. So the volume is going to be equal to pi times the square root of 16 minus, well, we want it in terms of, we have it in terms of x, we want it in terms of y. So let's go ahead and redo this, solving for x in terms of y. So we want to solve for x in terms of y. So we have x squared is equal to 16 minus y squared. So x is equal to the square root of 16 minus y squared. So because we're dealing with a very symmetric case, it doesn't change our function all that much. So let's just write down the volume here. So the volume is 16 times, the volume is pi. So it's pi times r squared, so 16 minus y squared dy. So now that we have our volume, we have to figure out what our force is. So force is going to be equal to our gravity times mass, or mass times acceleration, right? So ma, but our a in this case is going to be gravity, so gravitational acceleration, and our mass is rho v, our density times our volume. So our force at any point y is going to be our density, which is 800, our volume, which is pi times 16 minus y squared dy, and gravitational acceleration is 9.8, but to simplify things, let's just call it 10. So cleaning things up, our force function is going to be 8,000 pi times 16 minus y squared dy. So now that we've found our force function, we need to find our distance function. So the distance is going to be the distance between the ground and any point y. So we'll have y here. And the distance between the ground and the origin is going to be 5. So it should be 5 and something in terms of y. Now we would normally think it's y, but our origin is below ground and not the ground itself. So since it's below ground, it's going to be 5 minus y. And we can check this by saying the distance between the ground and the top, which would correspond to y equals 4, is going to have a distance of 1. So 5 minus 1 is or 5 minus 4 is equal to 1. And then at the origin, y is equal to 0, and there's a 5-meter gap between the height of the fluid, or the ground, and the origin. So that's going to be 5 minus 0, which is 5 meters, which makes sense. And then if we were to go from the ground all the way to the bottom of the sphere, which has a y value of -4, it should be 9 meters. Which makes sense because the whole sphere has a diameter of 8 meters, so we add another meter to it and we get 9 meters. So our distance function is 5 minus y. Our force function is 8,000 pi times 16 minus y squared dy. And that tells us that our work function is the integral from a to b of 5 minus y times 8,000 pi times 16 minus y squared dy. So all we really need now is to figure out what is our a and b. And what we have is we have y equals -4 because that's the bottom of the tank. There's always going to be fluid at the bottom of the tank if there's any fluid in there at all. And since our tank is half full, we're at the halfway mark, which corresponds to y equals 0 in our case. So going back to our sphere, we have -4 and we have 0. And if we fill that up with fluid, we see that half of the tank is filled. So that's going to set our bounds on our integral from -4 to 0. So we can pull out that 8,000 pi because it's just a constant, and we have on the inside 5 minus y times 16 minus y squared. We can FOIL it out, and we get 8,000 pi after integration times 80y minus 5y cubed over 3 minus 8y squared plus y to the 4th over 4. And we're going to plug in our bounds from -4 to 0. And that's just plugging it into a calculator or doing it all out longhand. And we finally get that our work is equal to approximately 7 times 10 to the 6th joules, which we can just write that as 7 megajoules. Thank you for watching. I hope this has cleared things up. If you have any questions, I know that things like pumping fluid out of a container can be kind of difficult. So if you have any questions, leave them in the comments. If I can't respond to them in the comments, I'll just make another video or refer you to some other resource so you can understand it better.